Alright, Assalamu alaikum. So, today we're going to start looking at statistical mechanics. We've already seen statistical mechanics in bits and pieces, but I would like to finish off on a discussion that we started in the previous lecture. And if you remember, we looked at two kinds of circuits, and we looked at a practical demonstration. If I had a diode or a PN-junction, and this was connected to a supply that supplied AC voltage, so current flows through this system. This is an AC voltage, and I would like to find out what's the voltage drop across this resistor. I observed a pattern which went as follows. So if this is my input voltage, this voltage that is being supplied to this circuit, so this is my time axis, and this is my input voltage, and the input goes positive, negative in a cyclic fashion. This is called an AC voltage source, an alternating current voltage source. So what happens in this case is that in the positive cycle, I can visualize this AC voltage source as a battery that is flipping its direction over half a time period. So in half a time period, from 0 to t by 2, this is the effective model of this source. And in the other half cycle, the polarity of the battery is switched. This is what an AC voltage is akin to. So the AC voltage is akin to a flipping DC voltage. But not only a flipping battery, but the amplitude of this voltage source is also changing in a sinusoidal fashion. This is what an alternating voltage really is. So in half of the cycle, in this half of the cycle, the positive terminal of the battery is connected to this P terminal of the diode. So this triangle represents the P terminal of the diode, the P-type material inside the diode. This stroke represents the N-type part of the PN diode crystal. So in this part of the alternating source, the positive terminal of the battery is connected to the P. And what happens is that a current flows during the cycle. And when a current flows, a voltage is dropped across this resistor. And this voltage will be proportional to the amount of current flowing. And the amount of current flowing will be proportional to the strength of this battery here. However, in the other half of the cycle, which I'm going to represent by pink inside this diagram, in this part of the cycle, the negative terminal of the battery is connected to the positive P terminal of the diode. And in that half of the time period, the diode does not conduct, it's shut off. So the current will not flow through the diode in this half of the cycle. And when the current doesn't flow, there is no voltage drop across this resistor. Alright? So if I were to trace out the voltage drop across this resistor, which is also called a load, and I showed a practical demonstration that this voltage across the load looked like a positive voltage following the amplitude of the input voltage, not exactly the same amplitude because it could be different. And in this negative half of the input, the voltage goes to 0, approximately 0. And then it follows, the positive half goes to 0, positive half goes to 0, positive half goes to 0. So you get an output which is called a rectified output. And in fact, it's a half-wave rectified output. So this diode is actually acting like a valve. it allows current to flow only in one direction, and it blocks the current through the other direction. It's like a valve. A one-way valve, a one-way street for the charge carriers. If we had a circuit, the other kind of circuit that I showed was a slightly more complicated circuit in which I had the same voltage source, and instead of a single diode, now I have four diodes, two pairs of diodes. So this is what my circuit looks like, and I am tapping off the voltage across this load resistor. This is what I am measuring. This is my V measured. Here, this is my V measured. Now in this circuit, what happens is that during half of the cycle, the current can flow through this diode, it comes down the diode, and it goes out through this diode and completes its path. In the other half of the cycle, when the negative terminal is connected here, the current takes the other path. It actually flows from this side of the circuit, goes through this diode, comes down the resistor exactly in the same direction as before, and then completes its complete circuit through this diode and goes down. So whatever the positive or the negative cycle is, the current is always flowing through the diode and is always flowing through the same direction. So if I look at the output across the load resistor, in this case, the current goes up, so the voltage goes up, comes down, and during the negative half of the cycle, current is still flowing through the diode. Through the resistor, and it's flowing in the same direction. So I get a multi-humped output across this load resistor. This is what you observed in the demonstration on the other day. So this is called a full wave rectifier. Now what we've learned in modern physics is we've learned a little bit about PN junctions, about charge carriers, about electrons and holes. So we would like to explain the behavior of these circuit elements, these diodes, in light of quantum mechanics, in light of modern physics. We would like to describe why do we observe this kind of behavior. Alright, so any questions about this circuit behavior? Hello. Alright, any questions about the circuit behavior? Now we would like to describe the circuit behavior. Yes? Yes, you need an inverter for that. You need a different kind of circuit for that. So this circuit is actually converting an AC into a DC. into a direct current. It's not a constant current, but it's a direct current. Excuse me. All right. So how is this diode formed? It's one crystal of a semiconducting material. You can't take a p-type material and graft it together with an n-type material and form a diode. This diode is constructed from a single crystal of silicon. And this crystal is grown. You grow crystals. And you grow crystals by a certain technique. There are different techniques of growing crystals. One of them is called the pulling technique. The key idea is that you have a single crystal of silicon, and this single crystal of silicon is grown in such a way that half of the crystal is doped in the P fashion and half of it is doped in the N fashion. Excuse me. Alright. So it's just one crystal. I'm not taking a p-type crystal and an n-type crystal and gluing the two crystals together. It's just one crystal which has been grown in such a way that during the growth, half of the crystal has p-type dopants and half of the crystal has n-type dopants. So I'm changing the admixture during growth. Okay? Now, if I have a p-type material, all of this is electrically neutral. A p-type material is also neutral, and an n-type material is also electrically neutral. But there are different kinds of charge carriers inside these materials. The p-type material has charge carriers which are mobile holes. So these are the absences of electrons. And these holes conduct electricity and they live inside the valence band. Alright? The mobile electrons inside the n-type material live inside the conduction band. So first of all, what I'm going to do is I'm going to give you a crystalline picture of how this diode behaves as a valve. And then I'm going to present an energy band structure. Alright? So what I'm trying to do is I'm trying to figure out why does this diode behave as a valve? Why does it conduct electricity only in one direction when it's biased in a certain way? Bias means that I'm applying a battery here and I'm biasing it. I am applying a voltage in a certain direction to this PN material. Now this is a picture of a diode. And these are the charge carriers. Remember that in addition to these mobile electrons, there are a large number of electrons inside the n-type material, but all of them are in the valence band and they do not contribute to conduction. So what I'm drawing here are only the electrons inside the conduction band. Okay? Now what's going to happen is, first of all, there is a higher concentration of electrons here and a higher concentration of holes here. And when I say an electron, I only mean the mobile electrons. There are many other electrons inside the crystal, but they don't contribute to conduction. So when I say electron in today's class, it generally means a mobile electron inside the conduction band. And when I say a hole, it means a hole inside the valence band. Alright. Now what's going to happen is that there's a higher concentration of electrons here and a higher concentration of holes here. And this is, but when I give you the diode, this is not the exact concentration. This junction has been formed, and when this junction is formed, we observe that this is like a compartment full of electrons and this is a compartment full of holes. The electrons must have the ability to diffuse out of this compartment because of the concentration gradient. It's just like opening a perfume bottle. You open a perfume bottle, there's a concentration gradient of the scent molecules and they're going to diffuse out of the atomizer of the scent bottle. Exactly in an analogous fashion, these electrons see a concentration gradient. They see a region devoid of electrons inside the p-type material. Likewise, the holes also see a concentration gradient. So just as any other process that you find in nature, whenever there's a concentration gradient, these charge carriers, since they are mobile, they diffuse. So first of all, I'm trying to see out what's going to happen at the junction. I observe that there is a concentration gradient and as a result there is some diffusion across the junction. So the diffusion is such that the electrons move towards the p-type material, they jump across the junction and the holes move in the opposite direction, also across the junction. So at the instant this crystal is being made, does this diffusion take place? It doesn't happen afterwards. It happens as the crystal is being made. So if I take a diode out of my pocket and present it to you, this junction has already been made and this diffusion has already taken place in the past. Okay? So I'm describing what has happened in the past. So with time, what's going to happen is that the region in the vicinity of the junction is going to see a change in the concentration before the junction is formed. This is my distance and this is the interface of the junction. Just before the junction is formed, I have a concentration gradient of electrons which is like a step function. This is the concentration of electrons. Concentration or density of electrons as a function of x. And this is a sharp step before the junction is made. Alright? Whereas if I were to plot the concentration of holes versus distance before the junction is made, this is what, it's a downward step. A sharp, abrupt change in the concentration of holes. However, now diffusion is allowed and across this junction some of the electrons inside the n-type material move across the junction and the region in the immediate vicinity of the junction inside the n-type material becomes devoid of electrons. Devoid means khali. It becomes devoid of electrons. This region in the immediate vicinity is now doesn't have electrons. Now it's given off its electrons. So the region to the right of the junction inside the n-type material acquires a positive charge because it has let loose its electrons. The electrons have diffused out. And it was neutral to start off with. So once the electrons have gone off, this region of the junction towards the immediate right acquires positive charge. And this region, which has let loose of its holes, acquires a negative charge. Okay? So I draw an interface of a positive charge. It's a positive charge, a real positive charge has been developed inside the n-type material to the right of the junction, and a negative charge has grown here on the surface of this interface. Let me erase this line to avoid any confusion, okay? So now there are still holes here because it's a large crystal and this junction is only at the interface. There are still electrons here. But this region acquires a positive interface and this region acquires a negative interface because this was electrically neutral to start off with and it has let loose its electrons. It has given off its electrons. When it gives off its electrons, it acquires a positive charge. Now if holes were to... Now what are the charges inside this, in between these Now new plates, so-called plates have been formed. A plate of positive charge or a surface of a negative charge. It's like a parallel plate capacitor has been built into the junction. The junction acquires a capacitance. It acts like a capacitor. Now what are the charges inside this crystal, inside this region of the crystal? No charge, because an electron has fallen into a hole. An electron inside the conduction band has dropped down into the valence band. So if I draw a band structure picture here, this was a hole to start off with. This is an electron. What's happened inside this region is that this electron has dropped into the hole and given off its energy. It can give off its energy in a multiple number of ways: light, photons, heat, phonons, the vibration of the crystal. It loses its energy somehow. This process is called electron-hole recombination. An electron has recombined with the hole. Now now what happens when this junction is being formed is, when will this process stop? When will diffusion stop? Right? Will diffusion go on forever? If diffusion goes on forever, this empty region, this void of charge is going to expand. It's going to bulge out as time progresses, because more and more charges are going to diffuse into this region, which is now deplete of all kinds of charge carriers. Deplete also means khali. So this region is also called the depletion region. This region is the depletion region. And this capacitor, this effective capacitor, is called a junction capacitor. Now will this process continue forever? If it's going to continue forever, all the electrons and the holes are going to interdiffuse, and this entire region is going to grow with time in space, and all of this will become the depletion region. But is there a limit to this? What's going to happen? When will this process cease, if it ceases at all? Is this process going to stop somewhere? Or it's going to carry on forever? What do you think? G. Okay, it's going to stop when? Why is it going to stop? Why is it going to slow down? Is it going to slow down? Yes, why? Suppose that the concentration of holes is extremely large to start off with, and there's an equal concentration of electrons, so all of these electrons can drop into holes and they can annihilate one another, so the depletion region can effectively spread out to the entire crystal. Yes? Yes? Exactly. So now this is negative charge here, and if an electron would like to come into the depletion region, what it needs to do, it has to go uphill. This negative charge is repelling the electrons. So if these electrons have to fall into the depletion region, they have to go against this negative interface. This positive sheet is going to repel these holes. So the diffusion of electrons and holes is going to be arrested as this charge grows up. This charge is growing up with time because the electrons and holes are recombining. And when they're recombining, the positive charge goes up and the negative charge goes up because these regions are becoming devoid of electrons and holes. So this charge is growing up, and as this charge is growing up, it's going to impede or stop or counteract the diffusion of holes, and this negative interface is going to counteract the diffusion of electrons. So there's a limit. And when the electron does not have sufficient energy to overcome this uphill, this uphill barrier, diffusion stops and equilibrium has been established. Now in the state of equilibrium, what happens is that this NE is no longer an abrupt function. This NE takes a downward slope like this. There's a gradient in the concentration of electrons across the junction. And likewise, there is a gradient, a slope. The sharp, abrupt changes in the concentration of charge carriers is smeared out. Okay, it becomes slightly smeared out, as we say. So the corners are smoothed out a little bit. Alright, so now a junction has been formed, and you can take a voltmeter. If you had the facility of doing so, you could take a voltmeter and plug the two leads of the voltmeter across the junction. You'll measure some voltage. And this voltage depends upon the initial concentration of the electrons and holes. For a normal PN junction made up of silicon, this voltage is about 0.7 volts. For germanium-based semiconductors, it's about 0.2 or 0.3 volts. So this is a junction voltage. Now it's pure diffusion, electrons and holes. The idea of electrons and holes is actually setting up a junction voltage, but we haven't applied a voltage to it as yet. There's no battery connected to this PN junction. So now we would like to connect a battery and see how this depletion region changes and how this conduction takes place actually. Okay? Now in this state, when I give you the diode, it's in its resting state, in a state of equilibrium. There is no current across the diode. Everything is in a state of equilibrium and a junction has been created. Okay? Now what happens in a solar cell, for example? Let me give you a brief idea of what happens in a solar cell. In a solar cell, a photon comes in, say from sunlight, some HF, some photon, this wavy line shows a photon comes in and it creates a pair of an electron and a hole. So photon comes in, it gives energy, and an electron is created in the conduction band and a corresponding hole is created in the valence band. So this is exactly the inverse of this process. This is the generation of an electron-hole pair. So a photon comes in, brings in energy has to be conserved, and it creates a pair of an electron and a hole. So electron-hole generation takes place. So inside this region, an electron and a hole can be created. Now this electron, if all the Fermi levels are adjusted, this electron can diffuse into this region and this hole can diffuse into this region, or the other way around, and can form a current. But this is the basic process. A photon comes in and generates charge carriers. This is what happens in a solar cell. It's the converse of what happens in an LED. Now we would like to bias this diode, which means we would like to connect a battery to it. Biasing means connecting a battery to a circuit element. First of all, we would like to forward bias it. Forward biasing means that I connect the P-type to the positive terminal of a battery. This is the P-type, this is the N-type. I still have holes here. And I have electrons here. Remember when I say holes or electrons, these are the mobile charge carriers. Now I'm going to bias this, which means I would like to connect this to the positive terminal of a battery, and I would like to connect this to the negative terminal of the battery. So electrons can flow inside this external circuit because these are metal wires. And in metal wires, electrons flow. The charge carriers are mobile, free electrons. Now what's going to happen is that this negative terminal of the battery is going to repel the electrons. These electrons inside the n-type material. And these electrons are going to diffuse into the depletion region, or they're going to drift into the diffusion region. Not diffusion. Diffusion is a natural process. This process of diffusion occurs naturally. It does not need a bias. However, now what's going to happen is that this negative potential is going to apply an electric field on these electrons. And the electrons are going to move under the action of the electric field. Okay? So when these electrons, and how will they move? They will move against the direction of the electric field, or in other words, this negative terminal of the battery will repel the electrons. This is what was going to happen by intuition, and physics matches intuition here. The electrons are going to drift into the depletion region. Now when this is going to happen, this region is going to become devoid of electrons because of electrons on a whole. This sea of electrons, this mobile swarm of electrons is going to drift towards the depletion region. So a positive charge will be built up on this side of this diode. This positive charge that is going to build up here is going to attract more electrons from the battery. The battery is a reservoir of electrons. Those electrons are being replenished by the battery. So a current is going to flow through the circuit. Remember, everything I'm actually describing this in a slow motion, as a slow motion picture, but everything is happening on the picoseconds time scale in a diode. Charges change. A positive charge occurs here, but then you have a feedback mechanism. A feedback mechanism or a control mechanism which would like to keep the charge constant here. Now if a positive charge grows here, the reservoir of electrons, which is the battery, which has created that reservoir out of a chemical reaction, is going to supply or replenish the electrons. They're going to flow into the circuit, and they're going to maintain neutrality on this side of the PN junction. So electrons are going to flow inside this circuit, and this is where you have a battery and a resistor. So if you have a resistor, electrons flow through the resistor. You can dissipate heat inside the resistor. You can do some useful work out of it. This is where the action is going to take place. The action is going to take place here, but you do something useful not inside the diode but outside the diode. On the other hand, what's going to happen here is that this positive terminal of the battery is going to repel the holes. Alright? In other words, these holes will now diffuse into the junction, into the depletion region. When they diffuse, this terminal of this side of the diode acquires a negative charge because the entire swarm of holes has now moved towards the junction. So this region acquires a negative charge because the holes are positive. They have moved out. This acquires a positive charge. So electrons are going, so what's going to happen? This requires a negative charge, an excess of negative charge. So what's going to happen to maintain neutrality here is that this negative charge has to flow out. So electrons will start flowing inside this circuit in this general direction. So this yellow arrow represents the flow of electrons. What's going to happen inside the junction region, inside the depletion region? Electron holes are now being flooded into the junction, into the depletion region. They have been biased into the junction region. They are now cascading into the junction region like a waterfall. So you have a waterfall of electrons into this depletion region and a waterfall of holes into this depletion region. And what's going to happen when a hole mates with an electron? It's going to actually recombine. And when it recombines, the electrons and holes, they are going to recombine, and as a result of this drift, this depletion region is going to shrink. So you have so we also need to figure out what happens, you are supplying electrons into the system and you're supplying holes into the system. Taking off electrons from the p-type is similar or tantamount, is the same thing as supplying holes into the system. So you have electrons coming in and holes coming in, but where are all these charges going? They are actually recombining here inside the junction region, inside the depletion region, and giving off energy. Okay? So if this were constructed as an LED, these electrons and holes that are going to recombine, they're going to give off photons, going to give off light. And this diode may actually emit light if the semiconductors are of the right material and the light is in the visible regime. If you would like to have a visible LED. So this is what's going to happen. And the charge is constantly going to flow through this external circuit. So you have a battery here, and you may have a resistor here, which acts as a load. And charges are going to flow in this general direction. And if I were to look at conventional current, the conventional current flows in the opposite direction to the flow of electrons. So this is the flow of the conventional current. So when you forward bias this diode, conduction takes place. As a result of conduction, this depletion region is shrunk. Because this negative charge is going to repel this, this negative terminal of the battery is going to repel these electrons and they're going to move towards the depletion region. So this region is going to shrink. And when this region shrinks, you have a smaller depletion region. The depletion region has now shrunk in. So this is what happens during forward bias. In reverse bias, the exact opposite happens. Yes? Sorry? Will this process ever stop? When will it stop? When the battery is depleted. Alright? Yes?
So one question, when you're saying that the electron-hole recombination is going to increase as the charges keep on moving, shouldn't the depletion region, the size of the depletion region increase? Because the amount of electron-hole recombination is also increasing.
So in equilibrium, the rate at which electrons and holes are recombining remains constant. Electrons are constantly being fed in at a constant rate because the current is constant. Holes are being fed in at a constant rate, so the rate doesn't change with time. The depletion region actually shrinks because now it's easier for the electrons to go towards the depletion region, which means that this voltage that is set up here shrinks because now the electrons find it easier to go across the interface. So you see in this case there is an electric field inside this region. The direction of the electric field is this, positive to negative. So what this does is that the holes would like to move, they find it difficult to move towards the interface. And these electrons find it difficult to move towards the interface. Now there's a voltage here. Now if the electrons in here find it easier to move towards the interface, then it really means that this positive and negative charge is coming down. Or you can also think that this voltage here, this electric field has a certain voltage associated with it, like 0.7 volts. If this voltage is higher, then the holes will find it more difficult to go across the interface. And if the holes find it easier to go across the interface, this voltage has actually dropped. And when the voltage drops, it is like the distance between these plates has gone down. Okay? Yes? Oh, let's forget about tunneling for the moment. Yes? With time means at the instant that the battery is connected, everything happens on a picosecond to nanosecond time scale, and then the junction width, the depletion width becomes fixed. So the time with time means it's happening in the wink of an eye, in less than a nanosecond. That's the time scale that we're talking about. And equilibrium is quickly established. Okay? Yes? What do you mean? The system as a whole is neutral, but there are regions inside the crystal that can acquire a charge. No. This is in a state of equilibrium. This crystal is neutral. This crystal is still neutral on a whole. This region is neutral. These electrons don't mean that this region of the crystal is negatively charged. These electrons are mobile and they only exist inside the conduction band. And they are, right? Because these electrons have been supplied by some dopant atoms, like arsenic atoms here. The arsenic atoms themselves are neutral. And when they come into the crystal structure, into the lattice, their electrons, there's one extra electron that is required to bond with the neighboring silicon atom. And that electron becomes a free electron inside the conduction band, but the arsenic, the dopant is neutral, and the host, the substrate, the matrix is neutral, so everything is neutral. So here everything is neutral. Even though I've drawn an electron, it doesn't mean that there's a negative charge here. Now, in a neutral crystal, electrons have gone out. That's where this positive charge region comes in. So this region is positively charged. And this region is negatively charged. And the amount of positive charge here must be the same as the amount of negative charge, so the system as a whole is still neutral. Right? So regions become positively or negatively charged, but the system as a whole is neutral. Why? This region? No, because it's not positively charged. It's neutral. So I have a silicon crystal. I give you a crystal of silicon. Is it charged or neutral? And if I put in, say, gallium atoms or arsenic atoms to p-dopate or n-dopate, the atoms themselves are neutral. And if I add these neutral atoms to a neutral substrate, will the crystal be charged? No, everything is neutral. Right? The dopants are neutral, the substrate is neutral. However, this region on a microscopic or nanoscopic or mesoscopic scale acquires a positive charge, and this region acquires a negative charge. This is real charge. Yes, this was a question at the back. So in reverse bias, what's going to happen is the exact converse of the process that we've already seen. This is the p-type, the n-type, and I put a negative terminal of the battery here. Now I have holes here, and I have electrons here. Now this positive terminal of the battery is going to attract the electrons. So these electrons are now going to be attracted in this general direction. What's going to happen as a result is that the electrons, the entire swarm of electrons is going to be shifted towards the right. Okay? And now this positive charge here, as a result, this region is also becoming devoid of electrons. So this positive charge, this sheet of positive charge that has been constructed across the junction is also going to shift towards the right. Because all the swarm of negative charges, electrons, is going to shift towards the right. And as a result, this junction grows, this depletion region grows. Likewise, these holes are now being attracted by this negative terminal of the battery. Now, if these holes are being attracted, this entire swarm of holes is being attracted. So this region, which is negatively charged, the holes are moving further away from the junction. When holes are moving further away from the junction, this negative sheet of charge is also going to sway towards the left. So this depletion region grows in size. Okay? And this process immediately stops because there is no charge drift across the junction. In order for current to flow through the external circuit, you have to recombine electrons and holes. It's not possible that you're supplying electrons into this circuit and supplying holes into the system or drawing electrons out from the system. With electrons and holes, they cannot just grow up or pile up inside the diode. They have to recombine. But they only recombine inside this region. Now this region is now bigger in size. It's bigger in size and there is no drift of electrons and holes into this interface, so conduction doesn't happen. It's only that this junction grows in size. The depletion region grows in size. No electron-hole recombination takes place, and there's no possibility of a continuous stream of electrons into the system. So there's no charge conduction inside this external circuit. In other words, in reverse bias condition, the diode doesn't conduct. Right? The depletion region has now grown in size. Here the depletion region has shrunk in size. Why is that shrunk? Because this swarm of electrons and the swarm of holes move towards the junction region, and there's a greater possibility of constant recombination. And when constant recombination takes place, electrons are taken off from this region of the crystal and holes are taken out from this region, and those are replenished by charge carriers through the external circuit. Here, electrons and holes are not taken out from the system because they don't recombine. And therefore, electrons cannot flow through the external circuit because electrons and holes are not being taken off from the system. So in equilibrium, everything remains quasi-neutral, remember. There's neutrality that has to be maintained everywhere in steady state conditions. For example, in this wire is electrically neutral even though charge is flowing through this wire. If the current is constant. If the current is constant, means that electrons are coming in and electrons are going out at the same rate. This is what a constant current means. If the current were changing with time, what does that mean? More electrons are coming in and less electrons are going out, so there is a traffic jam of electrons here. That's when charge is being built up here. But if charge is not being built up anywhere, it means that there is a steady flow of current. But a steady flow of current means that there is no charge built up anywhere inside the circuit. So these are subtle points, and you'll learn more about these in electromagnetism course. Luckily I'm not teaching it. But this is what happens in forward bias and reverse bias. Forward bias, the diode conducts. In reverse bias, it doesn't conduct. So this is like a one-way street for electrons or charge carriers through an external circuit. Now one thing that I would like to point out here is, in the reverse bias, if I were to make a diagram of applied voltage V or VB, which is the bias voltage, and the current through the diode, when the bias voltage is positive, which means that the diode is forward biased, there is some current. And when it's reverse biased, there is no current. So ideally, what's going to happen is that in the reverse bias condition, there is zero current, and in the forward bias condition, there is some current. So what you really observe is that there is very little current up to a certain threshold voltage. And then the current starts to increase exponentially. Now this threshold voltage exists because in the forward bias condition, even before you connect a battery, there is a capacitance in here. There is an inbuilt voltage in here. And if you connect this to a positive terminal of the battery and this to the negative terminal of the battery, then the direction of this voltage, just consider this to be another battery with a positive terminal here and a negative terminal here. So you have to overcome this voltage. in order for the current to flow, and that's why you have a threshold voltage here. And then the current goes up. Now this is also because of statistical mechanics that the current goes up, but I'm not going to explain this. But in the reverse bias condition, a small current does leak through. Can anyone explain why is there a small current, a small leakage current in the reverse bias direction? Why can conduction take place in small, minuscule conduction take place in this case? Yes. Suppose it's perfectly pure. Pure means this is p-type and this is n-type. So these p and n's are also impurities, but these are desirable impurities. Well, exactly. In the n-type material, there are some minority holes. And in the p-type material, there are some minority electrons. Why do we have these minority charge carriers? Yes. Why are they formed? Exactly, due to the temperature of the system. You know that the electrons and holes, they have to cross a certain gap. If there is enough thermal energy, which means that kBT is larger than Eg, then automatically electrons and holes will be created. This is called thermally generated electron-hole pairs. So an electron will be created at the expense of a hole because there is sufficient thermal energy to promote an electron from the valence band to the conduction band. The thermal energy is bigger than this gap. So just because of temperature, you're at room temperature, this is a certain gap over here, these electrons and holes can be created. And they can be created inside the p-type material as well as the n-type material. There's no stopping that. Okay? In a p-type material, electrons will be created, and in an n-type material, electrons will be created, and holes will be created. So there are always some minority charge carriers, and for the minority charge carriers, look at this minority electron inside a p-type material. It's a minority electron, right? It has been thermally created. See the negative terminal of the battery. This electron is being repelled, so it moves towards the junction. This positive terminal of the battery repels these minority holes towards the junction. And inside the junction, these minority charge carriers can recombine. And when they can recombine inside the depletion region, they are just acting like charge carriers in a forward biased condition. So they will contribute to conduction. And that's why in the reverse bias condition, there is a small leakage current. Okay? And in a certain regime, there could be a breakdown effect as well. This is called a Zener diode. But I'm not going to describe this. And tunneling is important in some diodes. It's called a tunnel diode. Okay, but I'm not going to describe that. Now what I would like to do is I'd like to take a break. It's going to be a short break because we're going to shift gears and we're going to talk about slightly a different topic, and that is statistical mechanics.